Again, I welcome you. In this video, we'll be considering the power of a wave. As I said, this to aid your understanding, to help in your revisions and preparations towards examination. I'm Stephen Ikubani. We'll be looking at the relationship between wave energy and power. Recall that the last video we looked at wave energy. Now we're looking at the relationship between the two, wave energy and power. Then we look at the factors that affect wave power. We look at the physical implications of the parameters that we'll come across. Then we relate the intensity of a wave to the power of such wave, and we also consider numerical problems. The power of a wave. The average power of a wave is just the rate at which the average energy of such wave is transmitted. Just so I know that power generally is the rate of change of energy measured in watts. Likewise, average power of a wave is the rate at which the energy of the wave, the average energy of the wave is transmitted. And that is given as the expression you have. Here you have the expression average power P with average is rate of change of energy. Because it is average, that's why the term T instead of small t, which is period. So that is the time average power now relates to the average power for every cycle. And you know, period also relates to the time for one cycle. So the energy in one cycle of a wave and the period gives the average power. And from the expression E earlier, you know that it's giving us mil A squared omega squared lambda over 2, and you have our T, which can be further expressed or simplified as given in equation 2, and you have 1 over 2 mil A squared omega squared lambda over T. Again, mil is the linear density, which is measured in kilogram per meter. Your A is the amplitude measured in meter. Your omega is the angular frequency measured in radian per second. Your lambda is the wave length measured in meters, and T is the period, which is in seconds. And from there, recall that V, you know this right from secondary school, that V is equal to F lambda, and we know that F is equal to inverse of period. Is that not? 1 over T, inverse of period is F. So if you bring that expression here, that's why we have V, which gives us this from here. That's it. So that's the final expression. And from there, for a medium, this will be constant, the mil will be constant, half is also a constant. So what we have left is the amplitude, the wave angular frequency, and the wave speed V, or the wave velocity. So that is, the average power is directly proportional to the square of the amplitude, the square of the angular frequency, and the wave speed. That's what it means. So the factors that affect average power for an homogeneous medium, a medium, non-medium, will be the amplitude of such wave propagating in the medium, the angular frequency of the wave, and the wave speed. That is, the higher the wave speed, or the higher the angular frequency, or the higher the amplitude, then we have higher power. intensity of a wave. This is the average power of a wave that is incident on a unit area of a surface whose plane is at right angles to the direction of the wave. Do you get that? Let me help you with that. Average power of a wave. A wave is propagating, is coming. The power of that wave that is incident on, let's say this surface now is a unit surface. What does that mean? That is, the surface is 1 meter by 1 meter. That's what that means. 1 meter by 1 meter. Okay. And the plane is at right angle to the direction of the wave. So this is the plane of the wave. You see it? So the direction of the wave is like this. The plane is like this. Let me pick another color to help you illustrate that. The plane of the wave is like this. The direction of the wave is like this. This is it. So medicular. So intensity of a wave that is incident on just that unit area. Its surface may be big, but the amount of it that is incident on 1 meter by 1 meter unit surface area is what is called the wave intensity. But because wave is more of a spherical or is circular, it's not like a line, then you address the area of that surface where the wave will be incident in terms of sphere. That's for sphere. That's why we have 4 pi r square. That's the area of a sphere. That's the area of a sphere. You know, when the wave is coming, it is coming and it's coming out in 3 dimensions. Usually, wave is emitted in 3 dimensions. It's 3D. So we have the area of a sphere. You have our A capital. That's why I try to differentiate between amplitude and the area unit surface area. Amplitude, if you see the A is not bolding, so you will follow through in this video consistently. A is not bolding for amplitude and it's a bit slanting, but for the unit area it is not slanting, it's not italicized. Amplitude is italicized, unit area is not italicized, and it is bolding. It is not. So intensity again is the ratio of the average power to the unit area of a surface. So you have the average power over 4 pi r square, which is the area of a sphere. And what does that mean? If you take that for a constant average power, then what you see is that the intensity of a wave will decrease farther away from the source of the wave. That's what this equation now means. That is, intensity I is inversely proportional to the square or the distance from the source of the wave. So the farther away you are from the source of the wave, then the lower the intensity, and the closer you are, the higher the intensity. That relationship is called of such when you have a parameter inversely proportional to the square of that parameter. We call it the inverse square law. Now recall that P average is equal to what we have here, 1/2 mil A squared omega squared V. then and I equals to P average over 4 pi r squared. What's just written now. So if you now bring both together, so substitute your P average here, bring it here, simplify, you have equation 8. You have equation 8, which is this intensity again. You see the factors that affect energy, that affect power, that also affect intensity. The only difference is just that the intensity now varies away from the source. As distance from the source decreases, the intensity increases, as vice versa. And also we can express the intensity also as equation 9, and that's when you, instead of using the linear density now, we're now talking about the actual density, 3-dimension, rho, this, whose unit is kilogram per meter cube, unlike male, which is kilogram per meter. This is kilogram per meter cube. Okay, so you can easily relate with that, and you would be familiar with how I came about it here. Remember that male is kilogram per meter. That means it is mass over distance. Okay, so if you now have it, then you have your, what you have as 4 pi r square, the area of the unit surface. That means what now is m over 4 pi r cube. That's volume. So I have m over v. So that's why you have your rho. That's why you have your rho. So m over v, you have your rho. So that's why this disappears. So this, the male, and 4 pi r squared, that's what gives you the rho. Therefore, we know now that I is proportional to the square of the amplitude, that the intensity is proportional to the square of the amplitude, and also the intensity is proportional to the square of the distance from the source of the wave. Thus, you can also have the expression, equation 10, that is A is proportional to, inverse proportional to how amplitude is proportional to now, inverse proportional to the distance from the source of the wave. And now, interestingly, we can also obtain another expression for the intensity of the wave using dimension analysis. Okay, pressure or change in pressure. Normally, as wave propagates in a medium, there will be change in the pressure in that medium. As energy propagates, there's change in the pressure. So maximum pressure of a wave is given at this expression, rho, which is density of the medium, the wave speed of the medium, the wave speed, then the angular frequency of the wave, and the amplitude of the wave. Remember that pressure is mass, force over area. Pressure is force over area, and force over area is what? Newton per meter square. Newton will be what? Kilogram. That's Newton. Remember, kilogram. Then meter per second square. Newton is force, as mass, force rather is mass times acceleration. That's how you have this. So force over area, and area is meter square, and that will give you kilogram meter per meter, then per seconds. That's for pressure. That is for the maximum pressure. Then if you now switch these two one by one, look at it. Density is kilogram per meter cube, then wave speed v is meter per seconds, then angular frequency is per seconds, and amplitude is meter. So if you look at it, we have kilogram meter squared over meter cube. We have then per seconds. We have per seconds square. Do you now see? So anywhere you have this expression in our previous equation, you can substitute the maximum pressure there. So let's go on. So thus, if you do it, we go back to our previous expression. We can remember our previous expression. We have I equals this omega squared A squared V. So separate over 2. So bring rho 1 omega out, 1 A out, and the V. You have 1 omega left and 1 A, then over 2. So this one here expression now, what gives you the change in maximum pressure. So very easy to deal with. Remember the dimensional analysis. So that's what to use to confirm that. And also, you can also manipulate again, so that you will also obtain equation 12. So any of the parameters given for intensity can be used to estimate the intensity of a wave, depending on the parameter that is given. If you are given the maximum change in pressure, then you can use equation 11, equation 12. But if you are not given that, are given other parameters like the density of the medium, the wave speed, the wave intensity, the wave frequency of the wave, amplitude of the wave, then you have to use the previous formulas. Let's see examples. Now, a small source of sound emits energy uniformly in one directions. For a particular frequency, the intensity of sound at a distance of 1 meter from the source is 1 exponential minus 5 watts per meter squared. From the unit, you now know that this is intensity, and this is distance, and corresponds to an amplitude of oscillation of the air molecules of 70 micrometer. Assuming sound is propagated without any loss of energy, we find the intensity of the sound and the amplitude of oscillation of air molecules. Now, when the distance is now 5 meters from the source. So, at distance of 1 meter from the source, we have the intensity of this and the intensity of this. And sorry, an amplitude of this. Now, if the distance has now increased to 5 meters from the source, we now to estimate the intensity and also the amplitude of the material in that medium, the molecules of oscillation. So you do this. Now, since the medium, there is no lot of energy and the same medium, then we assume that these parameters here are constant. So remember, this is mil omega squared a squared v over 4 pi r squared. But since it's the same medium, so every other thing is a constant. I'll represent as k here. So k here. So the first case, I1 is given, I1 is given. In the other case, I2 is not given, R2 is not given. We have to look for I2 and R2, estimate R2 and R2. And because they are the same medium, just equate them. That means the parameters are constant, the wave speed remains the same, no energy is lost. That's the essence. They say without any loss of energy, that means the wave speed remains the same, the amplitude of the wave the wave speed remains the same, the frequency of the wave remains the same, then the density of the medium. So this is a shorter approach to it. If you equate it and you make I2 subject formula. So we have I1 R1 squared over R2 squared. That is, for I1 is known, R1 is known, R2 is known. We have to calculate I2 for the known R2. So you substitute and you have 4 exponential minus 7 watt per meter square. So for the B part, we also have this expression. Put our K. So A is equal to K over R and K is equal to AR. So if K is AR and the medium is unchanging, then A1 R1 is equal to A2 R2. Also make A2 so here's the formula. So we have this. Now that R2 is also given, then you just substitute 70 micrometer. Micro means 10 to the minus 6 meter times 1 meter over 5 meter. You have your 14 micrometer. 14 which are minus 6 meters. You have that. A point source emits sound with an average power output of 80 watts. Find the intensity 3 meters from the source, and the distance at which the intensity of the sound is 1 to the minus 80 watt per meter squared. Now, a source of wave emits wave, a particular wave. Its wave is now sound wave, and it emits that wave, and the average power at the source is 80 watts. 80 watts. That's average power. Now, what will be the intensity at 3 meters from the source? And at what distance will the intensity of the wave be this? Recall that we said intensity is related to power. Is that not? Power, average power, and the area, which we said for a wave that is a sound wave is usually spread out. Sound is spread out. So we have this. Sorry, squared. So the area density. So we have this surface area. Then your expression is I equals 80 watts over 4 times 22 over 7 times 3 squared. It's just very easy, very straight away. Thank God all the parameters given are in standard units. Now the second part, P part, at what distance would the intensity of the what distance would the intensity of the sound wave be 1 to minus 8 watt per meter squared? Very easy to just make your R. So you have the formula, the expression. Make R your formula. You have this. You have that. So this P average over 4 pi I, everything square root. If you solve, you will have 25 kilometer, 5.226 kilometers. Again, an uncomfortably loud sound have an intensity of 0.54 watts per meter squared. Find the maximum displacement of the air molecules due to the sound wave if its frequency is 800 Hz. Then take the density of air to be 1.29 kilogram per meter cube and the speed of sound to be 340 meter per second. Now for this question, this is your wave speed, this is the density of the medium rho. It's not mil, this rho, it is kilogram per meter cube. Then your F is 800 Hz F. Then intensity is I. Calculate the maximum displacement, which is the amplitude. Let's see it. We have that. From this expression, give the parameters. This is the most suitable expression for that. Then make A your subject of formula. If you do that, your A becomes square root of 2I all over rho squared omega squared V. And remember that omega is 2 pi f, 2 pi f. So that's what we have here, 2 pi, our f is 800, then everything squared, or it's omega squared, and you press it and you obtain the amplitude. Okay, and that's 9.87 micrometer. 9.87 is power 6, and that's micrometer. Another example, a small loudspeaker at a concert produces a power of 25 watts. If the sound energy from the speaker passes through the surface area of a sphere of radius r, which is 5 meters away from the speaker, what will be the sound intensity at this distance from the speaker? Again, before I show you the solution, look at it again. The average power is 25 watt. Now the sound energy passes through the surface area, and we have to calculate the intensity. Now let's assume this is sphere. This is sphere. So a particular surface of the sphere, the wave pass through it. This is the source of the wave. The source of the wave. Okay, and this A1 is 5 meters from the source. What will be the intensity at this point? Very straightforward. With the formula we have already. We have that expression.